Hello and welcome back. We're continuing with our theme of illustrating our statistical lessons with abstract art from around the world. And today we'll look at art from Bangladesh. There's a reason I'm including abstract art. It's because I think many of you have been conditioned to believe that statistics are bewildering, complicated tangles of numbers, and they require a great deal of time and energy to sort out. Well, my hope is to convince you that the time and effort invested is well worth it, and that statistics, rather than making things more complex, that you will eventually realize it streamlines things, and it makes numbers simpler, more elegant. So once you get to the stage in your research where you actually formulate your research questions and begin to collect data to answer your questions, you'll be happy and confident that the application of your statistical knowledge will make things very smooth for you. In the last chapter, we learned about central tendency, in particular the mean score for a data set. You can think of the task of finding the mean as follows. Suppose I presented you with a data set and asked, what is the one single number that best represents this data set? The mean score would be a good answer in many cases, but if you have many people in your data set, it's not sufficient to summarize them all with a single number. We need to include an additional number or statistic to express something about the variety and diversity among the people in the data set. So to make a long story a little bit longer, that's why I chose to illustrate the chapter on variance with abstract art from all over the world, to highlight the idea of variety, diversity, and differences among people. So this is chapter 5.2. We'll be learning about variance and standard deviation. The variance and standard deviation will be partnered with the mean. In a similar way, previously we had paired the range and the semi-interquartile range with the mode and the median, respectively. As a foundation, we need a new way of expressing a person's performance on a test compared to other people who took the test. This is called the deviation score. That will be our first topic. Then we'll look at variance and standard deviation, and we'll do an interpretation. The deviation score is the difference between the raw score and the mean score. In other words, it's the raw score minus the mean score. Suppose we select one student from a classroom full of students. We can compute this student's deviation score using a math sentence. The subtle details of this math sentence or equation are important here. The lowercase italicized x represents the deviation score for our selected student. The uppercase X represents this person's raw score, and the uppercase X with a line or bar over it represents the mean score for the whole class from which the student was selected. And the order of subtraction is important, as will soon become clear. First, we'll find the mean score for this small class. So we already know the formula for the mean, so we can conduct the computation. We add up all the scores, we get 32. So the average x bar equals the sum of all the scores, and then we divide by the number of people in the sample. So we get 32 divided by 8 equals 4, which is the class mean. Now we're in a position to compute the deviation scores for each person. The uppercase X at the top of column 1 stands for the raw scores. The lowercase italicized x at the top of column 2 stands for the deviation score. How do we find the deviation scores? We'll first compute the mean of column 1 by summing the scores to get 32, and then divide 32 by the number of people, 8, to get the mean of 4. Now, subtract the mean of 4 from each person's raw score. And we have to look carefully at the details of this equation. Be sure to notice that the symbols for the deviation score is a lowercase x, and the symbol for the individual student score is an uppercase X, and the symbol for the group mean is uppercase X with a bar over it. Also notice the formula asks us to subtract the group mean score from each person's individual score. As a result, the deviation score will tell us how far each person's score is from the mean. If the person's score is greater than the mean, their deviation score will be a positive number. If the person's score is lower than the mean, their deviation score will be a negative number. For example, let's suppose Alex is the first person in our data set, and he has a score of 7 on a test. Alex's score is 3 points above the mean of 4, so we compute his deviation score to be 3. Person 2 is Bobby, and she has a score of 6 on the test. Bobby's score is 2 points above the mean of 4, so her deviation score is +2. Now let's jump down to the bottom score in the data set. This student is Charlie, and he did not study, and he wasn't prepared for the test, and he only got a score of 1. His score was 3 points below the mean of 4, so his deviation score is a -3. It would be helpful to have a summary statistic that gives us a typical deviation score. This kind of statistic would give us an idea how tightly or loosely scattered the scores are in a group of people in general. If the typical deviation score is small, we would conclude the scores are fairly tightly clustered. If the deviation score is large, we could conclude the scores are scattered widely from each other and widely from the mean. There is more diversity in a group when the deviation scores tend to be large, and less diversity in a group when the deviation scores tend to be small. If we simply average the deviation scores together, we'll always find in every data set that the mean is 0, as we found here. Add up all the deviation scores, divide by n, which is 8, and we're going to end up with 0. And this is not very helpful. The troublemakers in these computations are these negative deviation scores. So what can we do to convert them to positive numbers? We could take their absolute values, or we could square them. For algebraic reasons that I'll explain later, it's more useful to square them, so that's what we'll do. And once we've squared these numbers, all the numbers, they're all positive, and we can find the mean of these squared values. I hope you'll agree that this is a sensible thing to do. And when we compute the mean of the squared deviation scores, we get 3.5 as our result. You might argue that squaring the scores exaggerates the measure of diversity in the data set, and that's a point well taken, but we'll deal with that in a minute. Putting that problem aside, I hope you'll agree this is a good description of the variability in the data set. Recall, however, that we want to do more than describe the data in this particular sample. Our big picture goal is to describe the larger population from which the data came. And there's a problem with this step, as we'll see in the next slide. There's bias in the estimation. If we simply use the average squared deviation score from the sample to summarize the variability in the population, it will lead to an underestimation. We can correct this bias by decreasing the denominator in the estimate. So the next step requires us to decrease the denominator, or lower part of the fraction, by 1 point. By decreasing the denominator by just 1 point, we can correct the bias. This makes the sample value for the deviation just a little bigger, and this correction leads to a statistic called the variance, and we'll see this on the next slide. The symbol for variance is lowercase s squared, as shown on the left side of this equation, and the formula for variance is sigma lowercase x squared, so that's the deviation score squared, and the denominator for sigma x squared is n minus 1. And there's a formal algebraic proof that this small change corrects for the estimation bias, but we'll not go into that proof at this point. On the next slide, we'll look at an example of a variance computation. This time, instead of dividing by n, we'll divide by n minus 1, or 7, and we see that 28 divided by 7 turns out to be 4. But we still have a problem interpreting the meaning of this number, as you'll see on the next slide. So the problem with the interpretation of variance is that we found the variance to be 4, but we always need to provide a metric for our numbers that we derive. So for what? What's the metric or the unit for the variance? If x is in feet, so the raw score is in feet, and the mean of x is in feet, and the deviations from the mean, the lowercase x, are in feet, x squared is in square feet. So in the preceding example, the variance would be 4 square feet. Where are these 4 square feet? We can picture the location of the mean, but we cannot see the variance. The solution to this problem is to take the square root of the entire thing, and this will give us the square root of the variance, which is the standard deviation, and we are back to a metric that makes sense. In this case, it will be feet, and the value will be the square root of 4, or 2 feet. So we see the symbol for standard deviation is a lowercase s, and here is our formula, sigma x squared divided by n minus 1 entire, and take the square root of the entire thing. Another way to think about this problem is as follows. One could argue that by squaring the deviation scores, we inflated the amount of variance in the estimate. So to correct this, we undo the squaring operation by taking the square root of the variance. The square root of the variance is a new statistic that measures the spread of the data around the mean score. It's called the standard deviation. As I said, the symbol notation for standard deviation is lowercase s, and this statistic is our primary workhorse for the variation of a set of numbers. Here are the computations for the little data set we've been working with. And so we see that standard deviation equals the square root of sigma x squared. The x here is the deviation scores. Divide that by n minus 1. Plug in the numbers. We have the square root of 28 divided by 8 minus 1. Do the algebra. We have the square root of 4, and of course that is 2. So how do we make use of the information that the standard deviation is 2? We can use it to figure out the likely span of the data set. So we can use the estimate to figure out the extreme scores in the distribution with the following formula. X bar, which is the mean of x, plus and minus 3 times the standard deviation, will give us the extreme scores. We can identify where the extreme low scores are and where the extreme high scores are. The formula is the mean of x plus and minus 3 standard deviations. An extreme low score in any dataset will be 3 standard deviations below the mean, and an extreme high score will be 3 standard deviations above the mean. So let's look at some concrete. Suppose we're given the following information. We have scores for an empathy scale, let's call it test X, for a group of students. This group of students is called a norming sample for the empathy scale. A norming sample is a group of randomly selected students from the U.S. who represent the population of U.S. students. We want to find an extreme low score and an extreme high score for this group of students. The mean score for test X, or X bar, is 100. The standard deviation for test X in this group is 15. Then x bar plus and minus 3 times the standard deviation is 100 plus and minus 3 times 15. If we conduct the computations, we find an extreme low score in the group of students is 55 and an extreme high score is 145. Example 2 is a self-esteem scale. A psychologist creates a long diagnostic inventory to measure self-esteem and administers it to a norming sample. For the students in the norming sample, the mean self-esteem score is 500. The standard deviation is 100, and we conduct the computations given in the slide, and we find the extreme scores are 200 at the low end and 800 at the high end. So if we take the mean of x plus and minus 3 times the standard deviation, we have 500 plus and minus 3 times 100, and that gives us our extreme low and extreme high scores. So let's use our newfound knowledge to complete the extreme scores in our little data set from earlier in the lesson. So we see that the mean of our data set is 4, standard deviation is 2, so the mean plus and minus 3 standard deviations is 4 plus and minus 3 times 2, and that gives us an extreme low score of -2 and an extreme high score of 10. We see that our estimate overshot the extremes of our little data set. The actual high score was 7 and the actual low score was 1. But this is an artifact of the small sample size. With a larger data set and a data set that is normally distributed, we would come closer to the extreme score estimates with the formula of the mean plus and minus 3 standard deviations. But the estimates aren't too far off, and the formula did a good job of finding the extremes when we looked at larger data sets such as norming samples for the empathy scale and the self-esteem scale. So let's test your understanding. Question: a distribution of self-image ratings has a standard deviation of 0. What does that tell us about the individual scores? So if you think about how we derive the standard deviation, it is the square root of sort of the average squared deviation score, a little bit different than that. The only way this will be 0 is if every score has 0 deviation from the mean. And the only way this would happen would be if every score was equal to the mean. If every score equals the mean, everyone looks exactly the same in the data set, and there's no variety, no diversity at all. They're all the same. Let's test your understanding a second time. A distribution of well-being scores has a standard deviation of -3.87. What does that tell us about the data? Well, it doesn't tell us anything except the researcher has made a computational or reporting error. The variance and standard deviation can never be negative. They can be equal to 0 if everyone in the data set has the same score, but they cannot be negative. So now let's test your understanding a third time. Question: a distribution of arm lengths has a standard deviation of 2. A distribution of weights has a standard deviation of 10. Which distribution is more homogeneous? Now, when I talk about a homogeneous distribution, I'm talking about one in which all the data points in the data set are clustered closely together about the mean. A heterogeneous distribution is one in which there is a lot of dispersion or scatter in the data. The data tend to fall far and wide away from the mean score in both directions. Consider the following question that we have here about homogeneity. The answer is that we want to be careful not to jump to the conclusion that the homogeneous data set is the one with the smaller standard deviation. I want to be very clear that the standard deviation is sensitive to units of measurement. Thus, we need to know the units of measurement for height and weight in order to determine which is more homogeneous. So we would at least need to know the units of measurement. Let's give another example. Suppose we had a sample of 100 bamboo poles. We'll call this sample A, and we find the standard deviation of their lengths is 3. Then we have another sample of 100 bamboo poles, sample B, and the standard deviation of their lengths is 10. So the bamboo poles in sample A tend to differ from their mean length by a unit of 3. The bamboo poles in sample B tend to differ from their mean length by a unit of 10. Which sample has more variability in length? If you picture these two sets of bamboo poles, which sample in your mind appears more varied? You are probably thinking the sample with the larger standard deviation, sample B, is more varied. But then If I tell you the unit of measurement for sample A was in yards and the unit of measurement for sample B was in inches, you can quickly realize a standard deviation of 3 yards reveals more variability than a standard deviation of 10 inches. So sample A has more variability than sample B. As I've said before, the mean and standard deviation are very important. They are the lead actors in the world of statistics. In the lessons ahead, these two statistics will be featured as the star players. In the next lesson, we'll talk about the versatility of standard deviation. To extend our actor metaphor a bit further, we'll learn how the standard deviation behaves under specific instructions from the director of the movie. Suppose the director wants the standard deviation to undergo a linear transformation. How will the standard deviation behave under a linear transformation? You'll find out in the next lesson.